The science behind coral bleaching. Coral bleaching is a significant environmental phenomenon that affects coral reefs worldwide. Here's an overview of the science behind coral bleaching. Symbiotic relationship. Corals form a symbiotic relationship with photosynthetic algae called zooxanthellae, which live within coral tissues. These algae provide corals with energy through photosynthesis and contribute to their vibrant colors. Stress response. Coral bleaching occurs when corals expel their zooxanthellae or lose pigmentation, causing them to turn white or pale. This expulsion is a stress response triggered by environmental stressors, primarily temperature stress. Elevated sea temperatures, even by just a few degrees Celsius above normal summertime levels, can disrupt the coral-algae symbiosis. This leads to the expulsion of zooxanthellae, essential for coral nutrition and coloration. Light intensity. Excessive light, particularly ultraviolet radiation, can stress corals and exacerbate bleaching. Nutrient pollution. High levels of nutrients, such as nitrogen and phosphorus from runoff and pollution, can increase algal growth, shading corals and stressing them further. Consequences. Coral bleaching weakens corals and makes them more susceptible to disease, predation, and mortality. Severe or prolonged bleaching events can lead to large-scale coral mortality, impacting reef biodiversity and ecosystem health. Recovery. Some corals can recover from mild bleaching events if environmental conditions improve and zooxanthellae can recolonize coral tissues. However, recovery is slow and depends on factors such as water quality, temperature stability, and ecological resilience. Global impact. Coral bleaching is a global phenomenon exacerbated by climate change and ocean warming trends. Mass bleaching events have been observed worldwide, affecting iconic coral reef systems such as the Great Barrier Reef in Australia, the Caribbean reefs, and the Pacific reefs. Monitoring and research. Scientists monitor coral reefs using remote sensing, field surveys, and coral health assessments to track bleaching events and assess reef resilience. Research focuses on understanding bleaching mechanisms, predicting future impacts, and developing strategies for coral reef conservation and restoration. Mitigation strategies. Mitigating coral bleaching requires reducing greenhouse gas emissions to mitigate climate change, improving water quality through reduced nutrient runoff and pollution, establishing marine protected areas, and promoting sustainable coral reef management practices. Understanding the science behind coral bleaching is crucial for addressing the threats facing coral reefs and implementing conservation measures to protect these diverse and ecologically valuable ecosystems. Efforts to mitigate climate change and reduce local stressors are essential to safeguarding coral reefs and the numerous species that depend on them for survival.